Hello, this is Mr. Gilmore with the 2.7 Euclid's Theorem lesson. We are going to then finish off Chapter 2 by looking at these last two very famous theorems, one known as Euclid's Theorem and the other as Pythagoras' Theorem. Now, we'll begin our adventure into Euclid's Theorem today. However, we will discuss a little bit about what Pythagoras' Theorem will look like as well. So why are these so famous? Is because both of these propositions, both of these theorems, were proven indirectly. And since we have covered what an indirect proof is, then we'll take a look at why these are so profound indirect proofs, because of how we reach our goal. So we know the drill as far as how an indirect proof is set up. We still have a given statement and a proof statement, but then we jump into the assumption, where it's the negation of our conclusions, the negation of our proof statement. With that negation, we reach into then a reduction and find a contradiction. Now, with Euclid's theorem, Euclid did something very profound. He spent a lot of time working with this theorem. We'll see how he actually took his assumption and was able to reach a contradiction. Now, we will see there's a little bit of setup to Euclid's theorem as we begin the indirect portion of his proof. Now, there are two theorems that we're going to discuss, as I said earlier. We have Euclid's theorem and we have Pythagoras' theorem. Now, Euclid has a phenomenal proof that actually proves that the set of prime numbers is infinite. Think about that. If we were trying to prove something is infinite directly, is it even possible? No, because in order to prove it directly, we have to show it for every single case. Well, it would be then impossible for us to show that there's an infinite number of prime numbers, infinite set of prime numbers. Well, Euclid arrives at this conclusion indirectly. It's a brilliant proof. We'll take a look at how he unfolds this in just a moment. Pythagoras' proof is actually, what he proves is that square root of 2 is irrational. And that actually has a really neat anecdote that comes with it. So when we jump into 2.8, our last lesson on Pythagoras' theorem, I'll tell you a little story about how he came across this proof. So today we're going to focus on Euclid's theorem, and then the next lesson we'll focus on Pythagoras' theorem. So we're going to next then prove Euclid's theorem. But before we get into that, there are some relative terms, these definitions we have to jump into, and some basic facts that I want to remind you of. So the very first thing we need to establish is, what does it mean for a number to be prime, and what does it mean for a number to be composite? Well, we say that a positive integer is prime if it has precisely two divisors. That means it has the number 1 as a divisor and itself as the other divisor. So precisely two divisors. What does it then mean for a number to be composite? It means that it has more than two divisors. That would mean it has 1 itself and some additional divisor that divides into it. We're going to need to know that these two things exist, or these two terms exist, before we jump into Euclid's proof. Now, when we'll talk about this in a moment, we're going to be talking about sets of integers greater than 1, meaning we have the numbers of integers greater than 1, and what we're going to find is every number that is an integer greater than 1 is going to fall into one of these two categories. The number will either be a prime number or a composite number. There's not a number that will be both, and there's not a number that can't be that will not be neither of them. It won't be prime nor composite. So numbers will fall into one of these two categories. Now, here are two facts. Every integer greater than 1 is either prime or composite. This is what I just discussed. Why? Because every integer greater than 1 will have at least two factors. If it has 1 in itself, which means it has precisely 2, then it's a prime number. But if it has more than those two, 1 in itself and then another divisor, then it's composite. Here's another fact. Every composite is divisible by some prime number. Think about that. Every composite is divisible by some prime number. This follows from our fundamental theorem of arithmetic, which says that every composite has a unique prime factorization. Think about that. If you take a number, let's say 12, we can break it up into 2 times 2 times 3, or 2 squared times 3, which is its unique prime factorization for that composite number. So every composite is divisible by prime. So these two facts are going to help lead us into Euclid's proof that there are an infinite amount of prime numbers. So keep that in mind, that every number greater than 1 is either prime or composite, and every composite number is divisible by some prime. So here's where Euclid's proof begins. We want to prove that there is an infinite amount of prime numbers. Well, he does this indirectly, which means he assumes the negation of that. So what's then the opposite of there being an infinite amount of prime numbers? It would then mean there is a finite amount of prime numbers. So if there's a finite amount, that means that there is a countable set of prime numbers. That means we can start at p sub 1, representing our very first prime, and count all the primes we have in the set all the way up to the very last prime. Let's call this p sub n. Okay, because we've assumed that it's a finite set. So it stops at p sub n. There's no more prime numbers after that. That means we have all of the prime numbers in this set. So this is where then Euclid becomes absolutely brilliant. He uses what he now has assumed to reach a contradiction. So how does he do this now that he's assumed that there's a finite amount? So he says, okay, so we have this set of all these prime numbers. What should we do with them? So here's what he does with them. Step 2. He takes all of those prime numbers and he multiplies them all together. Right? So he takes all the set of prime numbers, which remember is finite, it's countable. It goes from p sub 1 all the way to p sub n, and it stops, and he multiplies them all together. And then he does something absolutely brilliant with all that. He takes the product of all those primes, and he adds 1 to it. Okay, so he just adds 1 to it. That's all he does, plus 1. So you take all your prime numbers, multiply them together, and then add 1. Because of this, now he has a new number. Let's call this new number S. So that means you find the product of all these prime numbers, add 1 to them, and we call that number S. Let's then dive into that number S that we've just created using our finite set of primes and adding the number 1 to it. So here is stage 3. Well, we know what the very first prime number of our set is, right? If we think about all the prime numbers we have, this is a finite set, we know what the first one has to be. It's 2. Now, since 2 is greater than 1, that means S has to be some number, some positive integer greater than 1 as well, because 2 is our smallest prime number, and that's already greater than 1. What does this mean for our number S? Well, this number S then must be either a prime or a composite. Think about what we said earlier. Any integer greater than the number 1 has to fall into the category of a prime or composite. So since S contains the factor of 2 in it, right, or has a prime of 2 in it, then we know it has to be an integer greater than 1, and that makes it either a prime or a composite number. So where do we go with that? So now, stage 4, we have determined that S is either a prime or a composite number. However, we're going to prove next that S can neither be a prime nor a composite. Let's unfold our assumption here. So let's say S is a prime number. If S is a prime number, well, then that's immediately a contradiction. Why? Because, so if S is prime, then S is a new prime, right? S is a new prime. But that's a contradiction. Why is that a contradiction? Because we assumed that we had all the prime numbers. Remember? That's what we assumed. We assumed that the prime numbers were finite, and we collected all of them. And we used them all to build S, which means S cannot be prime, because that would be a contradiction. Right? If S was prime, it would contradict itself, because we assume that there's a finite amount, and if it's new, well, that means that there's an additional prime to all the ones we collected. But we collected all of them already. They're finite, so there can't be a new prime. So S cannot be prime. So now let's assume, right, S has one other option. If it's not prime, then it has to be composite. Well, let's see what happens if we assume S is composite. So that means if S is composite, then what happens? Well, that means S must be divisible, oops, spelled that wrong, by a prime number. That is one of our basic facts, that if S is composite, it must be divisible by a prime number. But let's take a look at S's composition. S is composed, remember, of P sub 1 times P sub 2 times P sub 3, all of our primes, times all the way to our very last prime, P sub n, plus 1. That means if I were to try to divide P by any one of the prime numbers, so pick a prime number in this set, right? Pick a prime number. It would not be divisible because we would always have a remainder of 1, right? We'd always have a remainder of 1 because we added that plus 1 to the end of our product of all of our primes, which means we hit another contradiction. Because if it was prime, if it was composite, it has to be divisible by a prime number. But it can't be divisible by a prime number because we hit this remainder of 1 every single time. And it can't be prime because it then would be a new prime, and we've collected all the prime numbers. And that's, again, a contradiction. So what we've done then is eliminated the option for our number S. It can't be a prime, and it can't be a composite. So what is it? It is a number that doesn't exist. We've hit a contradiction by creating this number using finite amount of primes. Well, that can't happen now because if S cannot exist because there's a finite amount of primes, then there can't be a finite amount of primes. So our conclusion is this: since S is neither prime, or S must be either prime or composite, and since it can't be, then we've concluded we've had a contradiction there. So what then can we do with that? We can take our assumption and toss it out. It's hot garbage now, right? We cannot assume that there are a finite amount of primes, because if we do, we're going to reach a contradiction every single time with this setup. Every single time we'll reach a contradiction. So because our assumption is wrong, that there is a finite amount, we toss that out. So there's only one conclusion that remains, and that means there must be an infinite amount of prime numbers. A brilliant proof from our main man, Euclid himself. What a beautiful proof. Here's my advice. I am going to actually quiz you on Euclid's theorem and or Pythagoras' theorem. Okay, I haven't decided whether I'm going to do both or just one of them, but I will quiz you on Euclid's theorem and or Pythagoras' theorem. Here's what I suggest you do. I have uploaded Euclid's theorem into Chapter 2 module. I would suggest go there, study it, see if you can actually reproduce the proof. Meaning, do this completely from scratch. Start off with the conditional. Prove that there are an infinite amount of prime numbers. There's our conditional. Then move through each of the stages that we saw how they're set up. All right. Now, you may go ahead and already assume we know our terms and our basic facts are defined, such as we know what a prime number is and we know what a composite number is. And we can also go ahead and say we know our basic facts of that every number greater than number 1, every integer, I should say, positive integer greater than the number 1 is a prime or composite, and every composite has a divisor of a prime. You can go ahead and assume that. You're going to reproduce this proof. After you do it, check it with me, right? That's what you can do. That's how to practice this proof. So please go online, take my advice, and practice studying Euclid's theorem. What a beautiful theorem. Beautiful and brilliant, absolutely brilliant, proving that there are an infinite amount of prime numbers. Now, if you do have any questions, be sure to email me. But other than that, be good and do good.